Why is there a pressing need for improved solar energy solutions? This question is on the minds of many as we face a growing demand for clean, renewable energy sources. But before we delve into the depths of this topic, let's take a moment to understand the basics. Solar cells, or photovoltaic cells, are designed to convert sunlight into electricity. The magic happens when photons from the sun are absorbed, sparking an electric current through the photovoltaic effect. Traditional silicon-based solar cells have served us well over the years, but as our energy requirements continue to climb and the environment cries out for relief, the quest for more efficient solar cell technology has never been more important. Single-junction solar cells, predominantly made from crystalline silicon, have long been the industry standard, but they have their shortcomings. The most significant of these is the Shockley-Queisser limit. This limit confines the maximum potential efficiency of a single-junction solar cell to roughly 33.7% under one sun illumination. This theoretical limit exists because a single material can't absorb and convert all the photons across the entire solar spectrum. Enter the tandem solar cell, a promising solution to the efficiency limitations of their single-junction counterparts. These cells are built with multiple layers of different materials, each designed to absorb a specific range of the solar spectrum. By stacking these materials, tandem cells can harness a wider spectrum of sunlight, which results in increased energy conversion efficiency. Recently, perovskite solar cells have been making waves in the world of tandem solar cell technology. Perovskites are a unique type of crystalline material that can efficiently absorb sunlight and convert it into electricity. Here are some of the reasons why perovskite solar cells are a game changer. Perovskite materials have a high absorption coefficient. This means they can efficiently absorb a wide spectrum of light, including low-energy photons. This is especially beneficial in tandem solar cells, where the goal is to capture as much of the solar spectrum as possible. Another advantage of perovskite solar cells is that they're relatively easy to manufacture compared to traditional silicon cells. They can be produced using solution-based processes, which are cost-effective and scalable. Perovskite solar cells are also compatible with tandem structures due to their tunable bandgap. This means that by selecting the right perovskite material, researchers can design tandem cells that complement the absorption properties of silicon. This results in an optimal tandem configuration. The most exciting aspect of perovskite solar cells is their record-breaking efficiencies. They've achieved impressive power conversion efficiencies in a relatively short time, making them a strong contender for tandem solar cell applications. In conclusion, the potential of perovskite silicon tandem solar cells is vast. As we continue to explore and perfect this technology, we can look forward to a future where solar power is more efficient, affordable, and widespread. Harnessing the power of the sun has never been more promising. Can you imagine a future where solar energy is not only more efficient, but also more accessible and affordable? This isn't just a dream, it's a potential reality thanks to the development of tandem solar cells. Let us embark on a journey through time, tracing the development of these revolutionary devices. Starting from the initial concept, we find the roots of tandem solar cells in the established technology of silicon solar cells. Silicon, a material that is both abundant and stable, has served as a reliable foundation for the evolution of tandem cell technology. Fast forward to the present day and we find ourselves in the era of the perovskite silicon tandem configuration. This innovative design involves a perovskite solar cell stacked on top of a silicon solar cell. Each cell is fine-tuned to absorb different portions of the solar spectrum, thereby maximizing the overall energy conversion. The silicon bottom cell absorbs high-energy photons, while the remaining photons pass through and are absorbed by the perovskite top cell. This synergy significantly enhances the overall efficiency of the solar cell. The world of perovskite silicon tandem solar cells has witnessed remarkable progress in recent years. Scientists have achieved efficiencies exceeding 29%, a figure that rivals the performance of the best single-junction silicon cells. Furthermore, significant strides have been made in enhancing the stability of perovskite solar cells, a material notorious for its sensitivity to moisture and environmental factors. Innovative passivation layers and encapsulation techniques have been developed to protect the perovskite material from degradation, thereby increasing the lifespan of tandem solar cells. However, as with any advancement, tandem solar cells present their own set of challenges. The cost of production, while already more affordable than some alternatives, needs to be further reduced to make this technology a viable option for commercial use. Stability remains a concern, as more research is needed to ensure perovskite silicon tandem cells can withstand real-world conditions. Widespread adoption in the solar industry will require manufacturers and solar installers to adapt to this new technology, a transition that may involve regulatory changes and incentives. Lastly, integrating tandem solar cells into existing solar infrastructure and grid systems may present technical challenges. Despite these hurdles, the potential of tandem solar cells is undeniable. As we continue to innovate and overcome these challenges, we move closer to a future where solar energy is not only more efficient, but also more accessible and affordable. A future powered by the sun, made possible by tandem solar cells.
How much do we really know about the current state of solar energy and its boundless potential? It's a thrilling time with the advent of new technologies that are transforming the solar industry, and one of the most notable is the Perovskite Silicone tandem solar cell. So, what is a Perovskite Silicone tandem solar cell? It's a type of solar cell that combines two different materials, perovskite and silicon. Each of these materials has its own unique properties that allow it to absorb a different part of the sun's light spectrum. Silicon, a material that's been used in solar cells for decades, is great at absorbing the longer wavelengths of light. On the other hand, perovskite, a relatively new addition to the solar industry, is efficient at absorbing the shorter wavelengths. By layering these two materials together in a tandem cell, it's possible to harness more of the sun's energy. The perovskite layer sits on top, absorbing the shorter wavelengths, while the silicon layer sits beneath, taking in the longer wavelengths. This unique configuration allows these tandem cells to convert more sunlight into electricity, thereby increasing their efficiency. Indeed, the key feature of perovskite silicon tandem solar cells is their potential for high efficiency. Traditional silicon solar cells have an efficiency limit of around 25%, but with the addition of perovskite, this limit could be pushed to over 30%. That's a significant increase that could make solar energy more competitive with fossil fuels. Furthermore, perovskite silicon tandem cells are not just about high efficiency, they're also about cost effectiveness. Perovskite is a material that's relatively cheap and easy to produce, which could help to bring down the overall cost of solar cells. In summary, perovskite silicon tandem solar cells represent a significant leap forward in solar technology. They combine the best of both worlds, the proven reliability of silicon with the high efficiency and low cost of perovskite. As we continue to explore and improve upon this technology, it's clear that the future of solar energy is bright indeed. Stay tuned for more exciting developments in the world of renewable energy as we strive to harness the power of the sun to its fullest potential.